Hello friends, good afternoon everyone. In the last class, we discussed basic elements of translational mechanical systems. Hello friends, good afternoon. In the last class, we discussed about basic translational mechanical elements which are used for mathematical modeling. We identified spring, damper, and mass as the basic elements which can be used for building a mathematical model of a translational mechanical system. We saw a spring or a spring-like element, or an element which has a stiffness property which is similar to springs, can be modeled by using a mathematical equation. Spring force F is equal to K stiffness K into displacement X. And as we said in the last class, all these translational mechanical elements will have force as the input and displacement or velocity or acceleration as the output. This is what we saw in the last class. We'll move a bit further in analyzing the springs. If you're given two springs with spring constant K1 and K2, how to obtain the equivalent spring constant K equivalent for the two springs connected in parallel and in series. Now, as we are accustomed with this kind of arrangement, calling it as parallel arrangement and this kind of arrangement as series kind of arrangement, but as per Francis Raven's book, he calls this arrangement as series springs arrangement, and he calls this arrangement as a parallel spring arrangement. So the nomenclatures differ. Let us try to understand how we can build a mathematical model for series springs as per Raven's nomenclature, and how to build a mathematical model for parallel springs as per F.H. Raven's nomenclature. First of all, series springs. So we have two springs which are K1 having stiffness K1 and K2. These are subjected to external force F, and because of this external force F, they are subjected to displacement X. Please be attentive. Now, what we see here is that in this, I'm going to call this as series as per Raven's nomenclature only. In this series type of arrangement, what we observe is that both the springs which are in series are subjected to same displacement X, and this force is shared by each of the springs. Okay, so and in case of this parallel sort of arrangement, as per Raven's nomenclature, the springs having stiffness K1 and K2, these are subjected to force F. But as you can see, this force F is same for spring K1 and spring K2. Force F is same for spring K1 and K2, whereas this X1 and X2, the displacements will be shared. So overall displacement X will be summation of X1 of spring K1 and X2 of spring K2. So here small x, that is total displacement of this parallel arrangement, is X1 plus X2. Whereas if you come back to series arrangement, as I said, displacement is same. In this case, force is same. In this case, displacement is same. In this case, displacement is shared, whereas in this case, force is shared, right? So let us go to individual spring equation. Translation: two springs have same displacement. Okay, so I called it as, or as per Ravan's nomenclature, we call them as series springs. Okay. Otherwise, if you look at arrangement, those appear to be parallel springs. So no matter what we call them, what is important is how to write the equation. The two springs have same displacement, whereas the force is shared. So total force F will be summation of spring force of spring K1 plus spring force of spring K2. And as we know, spring force is given by stiffness K into displacement X. The displacement X is same for both the springs. So F is F of K1 plus F of K2. So F of K1 is K1 into X and F of K2 is K2 into X. So total force which is shared by both the springs is equal to K1X plus K2X. As the displacement is same, we can take it out common. So it is K1 plus K2 bracket multiplied by X is equal to F. And we can call it as K equivalent into X is equal to F, where K equivalent is equal to K1 plus K2. Okay, so this is what is the equivalent spring stiffness equation for, though I have written it parallel, appearance wise parallel, but as per Ravan's nomenclature, we are going to call this as series springs. So it is K equivalent for series springs, or this sort of arrangement is K1 plus K2. Suppose if you have got n number of springs arranged diagrammatically in parallel, but as per Ravan's nomenclature, number of springs are there, n springs are there, which are connected in series as per Ravan's, F.H. Ravan's nomenclature. If n springs are connected in parallel or as per Ravan's nomenclature series, then K equivalent, we can replace all the springs by one equivalent spring stiffness. Now this is for mathematical analysis purposes. Okay. So K equivalent will be equal to summation of K1 plus K2 plus dot 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 plus Kn. So 5 springs are there. K equivalent will be equal to K1 plus K2 plus K3 plus K4 plus K5. 7 are there. You have to go up K1 to K7. So it is simple summation of all the series springs as per Raman's nomenclature. As per diagrammatic arrangement, these appear to be parallel. Okay, what is important is K equivalent for series springs is K1 plus K2 up to Kn. Okay, now for so to say, appearance wise they appear to be series, but as per Ravan's nomenclature, we call them as parallel springs. What we said, force is same, force acting is same on both the springs, whereas displacement is shared. K1 shares X1 displacement and K2 shares X2 displacement. And overall displacement, if we call it as X, it will be K1X, it will be X1, small x, total displacement X will be X1 plus X2. Okay. So as we said, the forces on two springs are same, force F, however, displacements are different. So force F is equal to K1X, which is spring force for spring K1, and K2X2, K1X1 for spring of stiffness K1, and K2X2 for spring of stiffness K2. And if you solve it for X1, X1 will be F upon K1, X1 will be F upon K1, and X2 will be F upon K2. So displacement X1 is F upon K1 and displacement X2 is F upon K2. Since the total displacement X is equal to X1 plus X2 and we have F is equal to K equivalent into X. This is the overall equation. Force F is equal to equivalent spring stiffness K into X. Let us try to find out what is overall displacement X. Now overall displacement X for appearance wise series but Ravan's nomenclature type parallel. X will be equal to X1 plus X2. What is X1? X1 is F upon X is F upon K equivalent. If you solve this for X, X is equal to F upon K equivalent. So X is F upon K equivalent is equal to, what is X1? X1 is F upon K1 is equal to F upon K1. Next to is F upon K2. Let's go further. So F upon K equivalent is equal to F upon K1 plus F upon K2. Okay, so F being common, we can take out F from this side and F from this side, these get cancelled, and we have K equivalent. Let us just cross multiply K equivalent, right? If I take this K equivalent on right hand side, on one side, F is removed now. Once F is removed, 1 upon K equivalent is equal to 1 upon K1 plus 1 upon K2. So K equivalent taking on right hand side will be equal to 1 upon K1. This 1 upon K1 plus 1 upon K2 will go to the denominator. So K equivalent will be equal to 1 upon K1 plus 1 upon K2. If I just simplify this, what it will be? K1 plus K1 plus K2 upon K1 K2. So if I solve this, K1 or K2 plus K1 or K1 plus K2 upon K1 K2. So K1 K2 I can take it in the numerator. So it will be K1 K2 upon K1 plus K2. So K equivalent for parallel springs is equal to K1 K2 upon K1 plus K2. So if I have got n springs appearance wise in series, but as per Raven's nomenclature, those are in parallel. If I got n springs connected in parallel as per Raven's nomenclature, then K equivalent will be product of stiffnesses upon summation of all the stiffnesses. So K equivalent for parallel springs is equal to product of all the stiffnesses, K1 into K2 into dot 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 into K1 Kn upon summation of all the stiffnesses, K1 plus K2 plus dot 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 plus Kn. So this is how we can write equivalent stiffness for series and parallel springs. Okay, let us go to the second component, that is damper. Now the dashpot or the damper, if we just recollect, we talked about suspension system. The suspension system will have a spring and a damper. What the damper does? Damper, as the name indicates, damps the motion. The dashpot building block represents the types of forces experienced when they try to push an object through a fluid or move an object against frictional forces. So either I will have a damper proper, shock absorber sarka disnara damper, where there is a cylinder, there is a piston and oil, so that motion will be retarded, isn't it? Slowed down because of flow of fluid across the piston and cylinder wall, isn't it? It damps the motion. It is the work of the damper. Now, while modeling translational mechanical elements, will either have a damper proper, like the case of a suspension system. We talked about a motorcycle with a rider. We have mass of the motorcycle and the rider and the pillion rider, or that is the mass element, and then we have the springs, which we said we can actually have a spring, or we can have the tires, sponge, cushion, the tire or the rubber-like element which have a stiffness. Those are not actual spring, but those are spring-like elements. And then I have the damper-like element also. I will have damper proper in the form of a shock absorber, and I will have, taking the case of a motorcycle, I will have the inflated tube. Now that air is doing the work of cushioning. So the air, as the vehicle goes through a bump, goes over a bump or through a ditch, the tire being flexible, inflated tire, it gets compressed and the air gets compressed. So that air inside the tube provides me the cushioning effect. So that air becomes my damping element. Plus the seat on which I am sitting, the rider is sitting, which has got sponge beneath your seat, isn't it? So that also is doing the work of damping. So though it is not exactly a damper, but it is a damper-like element. So I'll either have a damper proper, or I can have damper-like elements. So what they do, they retard the motion so that we don't feel the pinch of the impact of the bump or a ditch, isn't it? This soft out that impact force, isn't it? So they dampen the transmission of forces, isn't it? So that is the work of damper. So as I said, in a translational mechanical system, I can either have a damper proper, fluid field shock absorber proper, or I will have damper like elements like inflated tube, like a sponge, or any of the lubricated joint, or a journal bearing having a grease. So all these are examples of damper-like elements. Though not damper, but they are damper-like elements. So what is the objective? To reduce the frictional forces, isn't it? The faster the object is pushed, the greater the opposing force becomes. The dashpot, which is used pictorial to represent these damping forces, which slow down moving objects, consists of a piston moving in a closed cylinder. This is a classical damper. Or, as I said, I will have a classical damper, or I might have damper-like elements, or which the elements which show damper-like properties. The movement of the piston requires the fluid on one side of the piston to flow through or past the piston. This flow produces a resistive motion. In the ideal case, the damping or resistive force is proportional to the velocity of the piston. So this damping force, if you call it as F suffix C is the damping force, is proportional to velocity. The spring force was proportional to displacement. The damping force is proportional to velocity of motion. And the constant of proportionality for this damping force is damping coefficient C. So F is proportional to V. V is nothing but dx by dt. Dx by dt can be represented by using an operator form called as d. This capital D corresponds to d by dt, isn't it? We have studied this in mathematics. Capital D corresponds to d by dt, and x is x. So dx corresponds to dx by capital Dx corresponds to dx by dt, which dx by dt is velocity. So the damping force F is equal to damping coefficient into velocity. That is equal to damping coefficient C into velocity dx by dt. That is equal to C into d capital Dx, where C is the constant damping coefficient. Larger the value of C, damping coefficient, the greater is the damping force at a particular velocity, isn't it? So C is equal to F by dx, isn't it? F by dx or F by V. So larger the value of damping coefficient, larger is the force required to overcome that damping force, isn't it? The greater damping force for a particular velocity. So this is the equation for a damper. Remember, we are studying mathematical modeling of mechanical elements. So damper is one of the elements. How the damper or damper-like elements can be modeled by using this force equation. Fc, damping force, is equal to C into V or C into dx by dt or C into capital D into x, isn't it? Let us move further. So translational damper, it is represented by this spring. As we said, we draw this big sketch of a spring damper. I show a piston and a cylinder. This is the symbol for a damper. When the viscosity or drag is not negligible in the system, we often model them with the damping force. All the materials exhibit property of damping to some extent. Not necessarily damper, but all the materials have this damping property. Even a shaft, though it appears solid, it has got porosity within, isn't it? So they also, though the displacements are very minimal, but they have this damping property, isn't it? If damping in the system is not enough, then extra elements, dashpot, are needed to increase the damping, right? External dampers are needed if the damping is not sufficient in the system. So common uses, these are the traditional dashpots or dampers. Door stoppers, we have seen, have a piston and a cylinder, or you might have a rotary hydraulic cylinder which damps down the motion of the door. म्हणून तो आपला दरवाजा आदळत नाही, isn't it? So we use door stoppers. In vehicles we use this the suspension shock absorbers, wherein this is fluid filled and you have a piston within, and the motion from the wheel to the vehicle chassis, this is connected. It damps down the motion. So bridge suspension in civil engineering applications also, as the vehicles move on the hung bridges, these are bridge suspension systems which provide the damping of these vibrations. Even in the flyovers, construction industry, flyover suspensions, as in today's era, all these flyovers are precast and assembled. As you must have seen, the conventional practice was to use conventional slab laying systems and waiting for months and years together. Now what they do is, as we must have seen, they just erect the column, and over the column we have a piece of road that is precast, and those precast road blocks are just placed by using cranes. Those are placed and they are joined together. Now, as these are called as modular structures, modular bridges. Even nowadays, civil engineers are constructing modular houses even. Those who are from Sholapur and Solapur area, if you just go through the Bantanal Mutt area, there is one Mada building which was constructed by Shirke builders from Pune and Bombay. Yeah, some 2 years back, they have constructed that building, which is probably 7 or 8 story building, just opposite that groundwater tank, just next to Bandramat. When you are moving towards Tirak Maharashtra Vidyapit or demand from this side, then you have on the left hand side, we have that building. That is also constructed. All the 7-8 stories are constructed in record time. It did not take conventionally, it takes months together, years together. In few months it was constructed. So all these slabs were precast and those were laid down on these columns, and these were bolted together, joined together. Okay, in such flyover suspensions also they use dampers. So these are the common uses of dampers, just for our information. We'll move further. This damper, just repeat of what we discussed earlier, is a piston, and the fluid passes through this narrow annular cavity, and the motion is damped. As the force is applied, the motion is damped, the change in position x. Now, how to write the transfer function and how to draw the block diagram for this damper. The damping force equation, as we discussed earlier, force is proportional to velocity v, and the constant of proportionality is damping coefficient, which is Newton second per meter or Newton per meter second raised to -1. So F is equal to C into V, or F is equal to C into dx by dt, or F is equal to C into dx. When I solve it for x, x will be equal to F into 1 upon CD. X is equal to F into 1 upon CD. So the transfer function we discussed. What is this transfer function? It is the ratio of output by input. Why this is called as transfer function? And why not efficiency? Because in efficiency, in the output side and input side, you have same units: power efficiency, transmission efficiency. Both the numerator and denominator have same units. Whereas in transfer function, the numerator output might have different units and input might have different units, as is the case, and that's why we call it as transfer function. So here I have displacement x as output and force F as the input. The units are different, Newton and millimeter, or Newton and meter, isn't it? So why to call it as transfer function? Force is transferred as x. Force is transferred as x, and hence the name transfer function. So our transfer function for a damper is output upon input. What is output? Output is x, displacement x, and input is F. So x upon F is equal to 1 upon CD, isn't it? 1 upon CD. So what is 1 upon CD? 1 upon CD is transfer function of this damper. Now, in the block diagram, if you recollect, last lecture also we discussed, the arrows show the signal. This is the input side, this is the output side signal, and this block represents the component. Either we write the name if I'm going to describe it. If I'm going to use it for analytical purposes, I put the transfer function values inside this block. You can refer a book by F.H. Ravan for more clarity. Automatic Control Engineering by F.H. Ravan for understanding all the concepts of control systems engineering. So, how to read this block diagram? Left to right. How do I read it? F into, what is the transfer function of dashpot? 1 upon CD. So F into 1 upon CD, F into 1 upon CD is equal to, right hand side is equal to X. So F into 1 upon CD is X. So this is the transfer function. This is the block diagram representation of a dashpot or a damper or damper like elements. We'll move further. Same thing, damper I have shown, single damper, applied force is F, displacement is X, F is equal to CV, F dx by dt, that is CdX, where C is the damping coefficient in Newton second per meter or Newton per meter second raised to -1. Let us quickly see the series arrangement and parallel arrangement. Similarly, this is appearance-wise, these appear to be in parallel, but as per Ravan's convention, these are in series. Okay, so similar to springs, applied force F and displacement X. Now, what happens here? The displacement experienced by both these series as per Ravan's convention. The displacement is same, whereas force is shared. So C equivalent in this case is C1 plus C2. So for series dampers, C equivalent is C1 plus C2. Whereas in parallel, as per Ravan's convention, appearance wise they appear as series, but as per F.H. Ravan's convention, these are called as parallel. So what is the case here? The force acting on each of the dampers is same, whereas the displacements or the velocities experienced by each of the dampers are different. So for this parallel damper arrangements, C equivalent is equal to product of damping coefficients upon summation of damping coefficients. So C1 into C2 upon C1 plus C2. Friends,